Hey folks, we're going to look at how you can figure out the direction of a net torque. This is going to be a little confusing, particularly when there's angles. First thing I want to mention is the way that this is phrased. It says, is the net torque about point A, etc., etc. When they say that, what they mean is make point A be the axis of rotation and imagine the object moving around that. That's just the way it's commonly phrased. So we're trying to figure out if the net torque is clockwise or counterclockwise. So we need to figure out how many of the torques are clockwise, how many are counterclockwise, how much they are. And if they happen to all cancel out, then the net torque would be zero. So I'm just going to sort of list which ones are which. We've got to just sort of visualize that. Now, if I find it easiest to draw in a radial arm, so I'm going to put in one here as a sort of dotted purple line. I'm looking at the force F1. So to draw a lever arm or radial arm, whichever you like to call it, just basically go from the axis of rotation right to where the force is being applied. I'll call that R. Now the force is pushing it sort of this way. It looks like it's going to move that clockwise. So torque from F1 is going to be clockwise. I'll draw in the other lever arms. For F2, that goes from the axis of rotation to this point here. Call that R. And this is not pushing it clockwise or counterclockwise. That's actually not going to even play into this situation. The angle between the force and the lever arm is 0 degrees or 180, however you look at it. Either way, the sign is 0 and it becomes unimportant. I'll draw in my final radial arm from the axis of rotation to F3. Now F3 is pushing it in a way that's going to sort of move the radial arm counterclockwise. So now we have to see if these are equal or which one's bigger. In order to do that, we're just going to be using our torque equals RF sine theta for each of these torques. So for F1, what's R? I got 2 units here. I don't know what they are. I'll just call it 2. So that equals 2 times F1. Now, these forces are all the same magnitude, we were told in the problem. It's not here, but on your homework sheet it is. So 2F sine 45. So that's going to be equal to sine 45 is 0.707, about 1.4-ish. I'll just call it 1.4F is our clockwise torque. That's the only one going clockwise, so that's the total clockwise torque. If there were more, I would just add them up. Now for F3, our R value is 3, and F is the same amount. The angle is going to be a little tricky here. So how can we figure out this angle from here to here? Well, let's see. I can figure out this angle, and this plus that angle will be 180 degrees. And let's see, I've got an opposite side is 1 and the adjacent side is 3. So the inverse tan of 1 over 3 is equal to, let's find out, 18.4 degrees. So that's this angle right here, which makes this angle 180 minus 18.4 is 161.6. However, the sine of this angle and this angle are going to be the same, so it doesn't really matter which one I use. I typically just go with the smaller one, and that's going to be sine 18.4. Sine of that is 0.31 times 3 equals about 0.95 F. Okay, so it looks like we have a winner. The larger torque is clockwise, and therefore the net torque is clockwise. Now, to provide an explanation of how I did this, if you don't have room to show everything in your explanation, could talk about using this equation for determining the amount of torque. So like I drew in the radial arms and determined the value for R from that and what the angle is. Use the equation to figure out how much torque there was and which forces have torque in which directions. So you want to definitely mention that F1 had clockwise torque of 1.4 F, while torque of F3 had a counterclockwise of only 0.95 F, which is less. And force F2 was pointed directly at the axis of rotation. The angle was 0 degrees, so it exerted no torque. That would be a good way to explain how we work this out. Now, the method that we had just looked at is definitely the simplest and most consistent way to determine a torque. It always works, but it can sometimes be a little more confusing mathematically, like figuring out that angle. There is another way. Now, if you're finding yourself very confused already, you might want to just skip this part. But if you're thinking, oh, that's fine, I'd like to see another way of determining these, then let's go ahead. I want to focus on the torque from F3. We had previously drawn in the radial arm from the axis of rotation directly to the point of application of the force. Now, there's another way we could do this that is completely equivalent, just not quite as intuitive in terms of understanding why it works. I don't have to draw my radial arm there. I can draw a radial arm anywhere I want. So what I'm going to do is I'm looking at that force and I want to draw a radial arm in a way that is perpendicular. So I'm making the angle be 90 degrees and then the angle just drops out of the whole thing. So the place I would do that is like I'm extending my force, at least direction-wise, along here, and then I would draw my radial arm perpendicular to that. So if I do that, my torque is RF sine theta, and by definition of the way we did this, this goes away. Now the radius is only 1 unit. I get 1F, which is a whole lot simpler to do the math. It's just a little harder to visualize. It comes out equivalent because we're shifting where the radial arm is, but obviously it's a smaller value, and then the sine of the angle becomes a bigger value. And that's always going to be proportional. We didn't get exactly 1 because I was using a calculator to do the trig functions, and those are not exact either, but it came out pretty darn close to 1.